Students, good morning. Today I am going to discuss about the development of relationship between overall mass transfer coefficient and the individual mass transfer coefficient. This is comes under the category of interface mass transfer. Today's class is very much useful in gas absorption studies. Clear? Gas absorption studies. So far we have been discussing about transport of molecules within a single phase system. There is no boundary between the phases, but while you go for industrial mass transfer operations, say for example absorption, adsorption, crystallization, distillation, drying, extraction, leaching and many other downstream process or industrial mass transfer operations, there will be two phases. So interface mass transfer is much more important. The knowledge on interface mass transfer is much more important. Now we are having a phase boundary or phase interface or interface. For this case, I am going to develop the relationship between overall mass transfer coefficient and individual or local mass transfer coefficient. For this discussion, we are in need of a simple experiment. Let us perform the simple experiment. In y-axis, this is x-axis. In x-axis, I am going to take mole fraction of component A in liquid phase. The notation is XA. In y-axis, mole fraction of A in gas phase. Mole fraction of A in gas phase. This is YA. The notation is YA. Clear? YA stands for mole fraction of A in gas phase. XA stands for mole fraction of A in liquid phase. Let us consider absorption of ammonia from ammonia air mixer using water as a solvent. Absorption of ammonia from ammonia air mixer using water as a solvent. The experiment is, take a saline bottle or a PET bottle. Visualize a PET bottle in your hand. Inject a known amount of pure water, distilled water in this PET bottle. Clear? Now the bottle contains only water alone. Again, now you are going to inject 100 ml of ammonia gas. Shake it well rigorously. Leave it for some time. Allow the system to attain the equilibrium condition. After the attainment of equilibrium, take the liquid sample as well as gas sample. Go and use the gas chromatography GC. Find the mole fraction of ammonia in liquid phase. Similarly, mole fraction of ammonia in gas phase. We have two values to locate a one point. Similarly, perform n number of experiments varying the volume of water, varying volume of amount of gas to be injected in the PET bottle. This experiment will give n number of values XA and YA. Clear? Right. The curve is called as equilibrium curve. This curve is called as equilibrium curve, or it is called as interface, phase boundary. All are similar. Clear? Now equilibrium curve is ready for the system of ammonia, air and water. Clear? Now leave it everything. Take a new PET bottle, inject known amount of distilled water, again inject the known amount of ammonia gas into the system. Now I have two new values used to locate one point. The point is called as, this is YAG. That means mole fraction of ammonia in bulk gas. This point is called as XAL, mole fraction of ammonia in bulk liquid. G stands for bulk gas, L stands for bulk liquid. Clear? Right. The intersection point with this equilibrium curve, this is called as YA star. That means mole fraction of ammonia in gas under equilibrium condition. Clear? This point of intersection gives XA star. This is mole fraction of ammonia in liquid under equilibrium condition. Now I have the bulk values YAG and XAL. Similarly, I have the equilibrium values, equilibrium condition. Under equilibrium condition, mole fraction of ammonia in gas phase, mole fraction of ammonia in liquid phase, and I am in need of the interface concentration, interface values. Now let me explain. We have three modes of transport. First, ammonia molecules gets diffused from bulk gas to the interface, one side of the interface, then crossing the interface, second step. Third step, from one side of another side of the interface to the bulk liquid. Movement of ammonia having three methods, three modes. One is movement of ammonia from bulk gas to the interface, crossing the interface, then interface to bulk liquid. Clear? For this case, I am going to write the flux equation. Clear? Na is equal to small k suffix y into YAG minus YAI. This is transport of ammonia from bulk gas to the one side of the interface for gases. Clear? Next, Na is equal to Kx XAI from interface to bulk liquid. XAL. This is for liquids. The thing is, the mid segment transport or crossing the phase boundary or equilibrium line, it is impossible to find the interface concentration by experimental method XAI and YAI. There is no chance to find the YAI value and XAI value by using any method of experimental procedure. Clear? Right. Now I am going to simplify the case. This is Na, this is also Na, so both are same. Ky is in Ky into YAG minus YAI is equal to Kx XAI minus XAL. So this is dy by dx format, YAI divided by XAI minus XAL is equal to Kx divided by Ky. This is the slope of operating line. Using this value, if Kx value is given or Ky value is given, if YAG and YAI values are given and XAI and XAL values are given, it is possible to find the slope of the operating line. That means this is slope of operating line M. Slope of operating line for gas absorption. Clear? This gives YAI, mole fraction of ammonia in gas at the interface. This is mole fraction of ammonia at the liquid side interface. Clear? If slope value is given or Kx and Ki values are given, it is possible to find out the YAI and the XAI. Practically, by experimental method, it is not possible. Clear? Next step. Now I am going to take bulk to equilibrium concentration. Clear? Next segment. YAG minus YA star. This can be written like this. YAG minus YAI plus YAI minus YA star. Clear? Say for example, from YAG to YA star, say for example this is 10. This 10 is equal to YAG to YAI, say for example 6. This is YAI to YA star, this is plus 4. So 6 plus 4 is equal to 10. Instead of writing YAG to YA star, I am going to write YAG to YAI plus YAI to YA star. This is the equation. Clear? YAG to YA star, YAG to YAI, YAI to YAL. For YAG to YA star, can be write like this: NA is equal to capital K small y into YAG minus YA star, the flux equation for this segment. Next, YAG minus YA, already it is written, YAG minus YAI, that is NA is equal to small k suffix y into YAI, YAG minus YAI. The new term YAI to YA star, YAI to YA star. Clear? Right. Draw a curve or line connecting with this interface to this one. Find the slope of this line. Slope will be m star. This m star is equal to dy by dx. That means YAI minus YA star divided by XAI minus XA star. Clear? Now the new term m prime is equal to YAI minus YA star divided by XAI to XAL. Clear? XAL. Now I am in need of YAI minus YA star. So YAI minus YA star is equal to m prime into XAI minus XAL. Substitute this information here. YAI minus YA star is equal to m star XAI minus XAL. XAI minus XAL, XAI minus XAL is equal to NA into NA is equal to KX XAI minus XAL. For this case, NA is equal to small k x XAI minus XAL. Substitute information 1, information 2, information 3 in this equation. Clear? For YAG minus YA star, I can write NA divided by KY. NA divided by KY. Small k, capital K suffix y is equal to, instead of YAG minus YA, I can write NA divided by KY. NA divided by small k suffix y plus, instead of YAI minus YA star, I can write like this: NA divided by KX. NA divided by KX with the operating line. Slope m prime. Again, NA gets cancelled uniformly. 1 divided by capital K suffix y is equal to 1 divided by small k suffix y plus m prime divided by k x. This is for gas phase relationship between individual coefficient and the overall coefficient. This is only for gas phase. Similarly, I can write the liquid phase equation. Okay, pause பண்ணுங்க. Right, coming to the point of XA star to XAL. Coming to the point of XA star to XAL. This can be written like this: XA star to XAI, XA star to XAI, and XAI to XAL. XA star to XAI plus XAI minus XAL. Clear? Right. XA star to XAL, I can write like this: NA, flux NA is equal to capital K suffix x into YA star, XA star minus XAL. Clear for this segment? What is this? XA star minus XAI, XA star, XAI, there is no information. Connect these 2 points. This is called as slope m double prime. For this slope dy by dx. For this slope dy by dx. dy means yag minus ya. dx means xa star to xa. So m double prime is equal to yag minus yai divided by xal. I'm sorry, xa star minus xai. Clear? I am in need of xa star minus xa. Hence xa star minus xai is equal to yag minus yai divided by m double prime. Instead of yag minus yai, I can write like this: yag minus yai is equal to na divided by small ky into m double prime. This equation becomes like this. Again, what next? This is xa minus xal. xa minus xal, this is the equation. Na is equal to small k suffix x, xai minus xal. From this equation, I can write like this: xai minus xal is equal to na divided by small k x. From this equation, I can write like this: xa star minus xal is equal to na divided by capital K x. Equation number 1, equation number 2, equation number 3. Substitute this information in this equation. For this case, na divided by capital K suffix x is equal to, for this case, na divided by ky, small ky m double prime, plus, for this case, na divided by small k suffix x. So unanimously cancel na value. So 1 by capital K suffix x is equal to 1 divided by m double prime into k suffix y plus 1 by kx, small ky. This is the equation for liquids relating overall mass transfer coefficient with individual mass transfer coefficient or local mass transfer coefficient. Clear? In the next class, I am going to discuss about the resistance to mass transfer. Clear? Thank you.